Okay, so how part C looks in your quiz is the following. So you will have to upload a file, or it's going to be a picture or a really good scan, or sorry, a scan or a really good picture of your resulting map from figure 5. Don't upload it until it's ready, obviously. In it, you have to have several parts to these questions. So you must have constructed the contour or potentiometric lines. Again, label them. You must have added the flow paths perpendicular to potentiometric lines from dry cleaners A and dry cleaners B. You must have added the flow path, so again, perpendicular to potentiometric lines from location X, which is where the rhodamine dye was poured, all the way to location Z, which is where it was detected 83 days after. And then you must also have the flow path from the dry cleaners that is causing the contamination to the residence in order to calculate the days that it must rely on an outside water source. So once you have those 4 things, you can go ahead and take a picture or a really good picture or a good scan of your resulting map and upload it onto this question. So as you can see, this is the highest weighted question of the whole lab because it's where you put most of your work. Okay, so question 13 through I think is like 18 or something in your quiz take you through the remaining questions in part C. For questions 16 and 17, again, you have to give me a numerical answer. I also specify here that do not include the units within these answers. This is just a number that I want resulting, and there is a range that I give you so that you're within somewhat relatively close of the answer that I put. Okay, I think that should be good for that. And again, question 18 is going to be both numerical and also short answers. So overall, I have it as a short answer. But because you do need to tell me how long after the cleaners is shut down would the residents be having to rely on the outside water source, you also have to give me some sort of mathematical operation of what you used using the rate that you have for question 17. So here you give me a short answer, so an explanation of what happens between the rate of surface water to groundwater flow, as well as some sort of mathematical operation to give me the length of time that it takes for the residents to be using other source of water. Okay, good. Question 17 of your lab quiz is gonna take you to part D. So let's go ahead and go through those questions. Okay, so again, that's the map from part C. Okay, so part D. Here we're talking about land subsidence from groundwater pumping. So we did talk about this in lecture somewhat, so this shouldn't be completely foreign to you. So land subsidence is the lowering of the elevation of land surface by changing the underground structure. Common causes of land subsidence are pumping of water, oil, and gas from underground, dissolution of limestone aquifers, which are also causing sinkholes, and also the draining of organic soils. Land subsidence occurs in almost every setting worldwide. The appearance of sinkholes is most common in the news, but the slow effects of subsidence can be just as damaging to structures. In fact, I think I tell this in my natural disasters class, if you're interested. Land subsidence actually costs more than, I think it's earthquakes, volcanoes, hurricanes, and flooding combined in the United States. So all of those 4 natural hazards, if you combine the overall cost that it takes to remediate them or the effects from them, land subsidence actually costs us more than that amount to just remediate from it. So it's a major topic, or it should be a major topic for us to be concerned about. Okay, so groundwater loss is an especially important topic in the southwestern U.S. Figure number 6 shows nearly 100 years of groundwater observations in the San Jose Valley area where residents have seen extreme amounts of land subsidence, but now it is largely stopped. So in contrast, figures 7 and 8, both A and B, show that land subsidence and associated fissures continue to be a problem in the rapidly growing Phoenix area. So unfortunately, Ander asks these questions, and sometimes he refers to which figure or which map he's referring to, but sometimes he doesn't. So in the quiz, I specified which map the question was referring to, but here it's not. So I'll pinpoint it to you as we go through the questions. Okay, so first question, how has population growth affected groundwater pumpage? So in this case, he's referring to the San Jose area. So that would be the figures on page 129. So let's go ahead and look at them. Okay, so again, question was, how has population growth affected groundwater pumpage in the San Jose area? So for that, you should be looking at this bottom graph. Here you have population growth in the red line. You have urban pumping in the bluish line, and then you have agricultural pumping in the green line. So both of those types of pumping are from groundwater, just so you know. So overall, the pumping from either one, you should be comparing it to the population growth and telling me how it corresponds, or how they both correspond. Either one corresponds to the population growth that you saw throughout the years in that area. Okay, so question 20 of your lab manual says, when were water levels measured the lowest in the Santa Clara Valley? What population trend does this correlate to? So when you read this question, you should be referring to both of the diagrams. The second one to give you the population trend, but then the first one you should be looking at to give you the lower water levels that were measured. So in this case, the blue kind of shaded stuff, that is the depth to water, or in other words, the water level itself. Okay? So you give me a specific year or set of years where you think that that those happened. In the quiz, it's a multiple choice question, so you have a straightforward answer in that sense. But then you have to compare that to the population growth or the population pattern that you see for the specific time period or time period in between or after, somewhere like that. Okay? Okay. Okay, so for question 21, it says, determine the maximum amount of subsidence that has occurred in the Phoenix area since 2010. Is it possible to make this land rise back to its original elevation? And then, how did the land surface react to recharge in the San Jose area? So in this case, you're using both figures, or all the figures in pages 129, 130, and 131. The figure on page 130 is the one you're going to use to give me the maximum amount of subsidence that has occurred in the Phoenix area. So as you see here below in the legend, you have the amount of subsidence, and given the specific color code that it has, you will calculate what the darkest color code corresponds to in the legend. Okay, so there's a specific answer. Actually, this is a short answer, so you'll have to be specific about it. Your lab manual is much easier to use than this video for that sense, because you can see the colors a lot more clearly. And then once you have answered the subsidence amount, you will tell me whether it's possible to make the land rise back to its original elevation. We went through this in lecture, and also he hints at it based on the next question. So how did the land surface react to recharge in the San Jose area? So in the San Jose area, as you can see from these figures, there was a recharge actually done in 1963. So from 1960 to 1963, subsidence reached its greatest average rate. And after that, you can see that the reduced groundwater pumping and recharge using imported surface water has raised groundwater levels and effectively stopped land subsidence. That shouldn't be affectedly, should be effectively. Okay, so recharge happened after 1963 to 1966 or something, and since then you see that the water levels have increased. So has that had any change, however, to the land surface? And when you look at land surface within these two diagrams, you should be looking at this green line. So land surface is right here. As you see, it decreased a lot, like several meters. But then once recharge started occurring, it kind of leveled off. It didn't really rise back. So that helps you answer question 21. Okay, question 22 says, reduced water pumping and increased artificial recharge were implemented in the 1960s. So that's what I was referring to over here. This is in San Jose. How has this affected the water levels? So then you basically examine this and you tell me what is going on after this 1960s policy started. Okay, question 23. How has the overall pattern of subsidence changed when you compare the 2013 and 2015 map to the 2014-2016 map, and that should be in the Phoenix maps. So that should be these two maps on page 132. You compare the amount of subsidence between the two maps, if there has been more or less, and maybe you should consider areal extent as well, if there has been more or less subsidence areally. So in the area, that's what I mean. Okay, question 24. So are there any major urban features that might be affected by the subsidence? And this is also in the Phoenix area. What types of features and what specific sorts of impacts might the subsidence have? So I think that's fairly straightforward for you to answer on your own. I think in the quiz, there are multiple answer questions. Question 25 is also a multiple answer question. What other surface features might you expect to see in this area that suggests land subsidence? So you should be thinking about the concepts that we saw in lecture. What can you see in the ground that may suggest that there is land subsidence? Okay, so I'll leave it up to you. And then the last question is, based on this information, what will you recommend to city managers about water usage in the area? So that would be city managers again in the area of Phoenix. What changes could they make in order to reduce this subsidence, or at least change it if this is how much you're seeing in a few years? And that's a short answer question. So again, let's go back to the quiz really fast to show you how those last few questions of part D look. So again, question 17 is going to be a short answer, or that should be question 19 from your lab manual. Questions 18 is a multiple choice. Question 19, short answer. 20 and 21 from your quiz, or 22 and 23 from your lab manual are multiple choice. Questions 22 and 23 or 24 and 25 from your lab manual are multiple answer. And then the last question, again, is a short answer that you make suggestions about any changes that the city managers should do about the water usage in the area. Okay, so as you can see, this is a long lab. I understand that it's long, and I know that it is long, but I think it is all concepts that are useful, not just for you to know, and not for me to only grade you on them. But they're also good for understanding what kind of situation we live here in the Western US and what kind of usage we should do to our water. So as I said in the lecture slides, water is a precious resource. We take it for granted many times, but it is precious, especially here in the West. So however we can save water, we should go ahead and do so. Okay, so with that, we are done covering chapter or whatever lab on groundwater. If you need any help, as always, I am here. You can write me emails, or you can communicate with me through the Blackboard Collaborate Ultra hours, or we can set up some sort of meeting as well on Zoom if you prefer that medium. Otherwise, have a good week. I hope that everything is smooth and that you do well. Have a good one.